Okay, good morning students once again. So here we are with the continuation of the work, energy and power chapter. Okay. Now till now you have discussed different forms of energy. You have discussed kinetic energy. You have discussed gravitational potential energy, elastic potential energy. Okay. Now this particular video is primarily to discuss one more aspect of kinetic energy. Okay, whenever a body is moving, it is obviously supposed to have kinetic energy, which is given by the formula half mv square, as you have already been taught till now. Now there is another parameter that we will study over here. First we have momentum. Okay, now momentum is a product of mass and velocity of the body. Okay, so if a particular body has a mass m and it is moving with a velocity v, okay, then the product of the mass and the velocity will give you what is known as momentum. Okay, now momentum obviously can be linear momentum, angular momentum. Okay, so we are not going to go into the details of those. For the time being, kindly note that the momentum is the product of mass and velocity, obviously for a moving body. Okay, as long as the velocity exists, okay, only then the momentum will exist. Okay, so we have two different formulae related with the velocity or the motion of a body. One is in terms of the kinetic energy of the body, which is half mv square, and the other one is momentum, which is represented, as you can see over here, with the letter small p. Okay, so small p, which will denote momentum, is the product of mass and velocity. Okay, now obviously the next question that will arise in our minds is that when we put the values of mass and velocity and calculate the value of momentum, momentum should also have its own unit. Okay, so once again, as it is important always, we study the SI unit of momentum, which will be, again, if you don't know, you will get it from the formula. So mass has a SI unit of kg and velocity has the SI unit of meter per second. Okay, so since it's a product of both, therefore SI unit of momentum will be kg meter per second. Please remember that. Okay, now the next thing that we move on to is the relationship between kinetic energy and momentum, because this may be used in some of the numericals that we may come across. Okay, and it is given in the book also, so you can just have a look quickly. Kinetic energy is equal to half mv square, okay, which can be further written as half mv into mv upon m. Now you see, how have we split this like this? We have a single m in the formula, okay, and since we have duplicated m two times over here, therefore we are going to divide this by m, so that effectively it is only 1 m which is there. Okay, and similarly v is already present in terms of square, so we have 1v over here, 1v over here. The reason why we have represented this formula like this is because mv, as you can see, mv, these are two mv's that are present, and mv is nothing but the momentum. Okay, so coming down further over here, kinetic energy is equal to half, this is this half, okay, p into p. Okay, so mv has been replaced by p in both places and obviously divided by m. Okay, so that gives you p into p square upon 2m. Okay, so your kinetic energy is equal to p square upon 2m. Okay, by doing all this, what we have done is, initially kinetic energy formula did not have momentum in it. Okay, so we have tried to bring momentum, which is p, into the formula, okay, without changing the formula itself. Okay, so cross multiply over here, this 2m into ke will become 2m ke is equal to p square. Okay, therefore p will become under root of 2m ke. Okay, this is the relationship between kinetic energy and momentum. Okay, so if you come across a problem in which you have to use such a formula, you can always go ahead and use it. Okay, now coming to some other questions once again. Now if you remember, in the previous video we had discussed a few numericals, okay, based on what we had done. Now again I have come up with a few numericals in this video also. Okay, all this, please remember, is for you to understand the way of solving different types of questions. Okay, you must solve lot of numericals on your own. if you are to practice, if you are to get a hold over the numerical solving part. Okay, so let us discuss a simple example based on what we have discussed over here. A body of mass 60 kg, okay, has a momentum of 3000 kg meter per second. So you can see kg meter per second has been used as the unit of momentum. Okay, so what are the two things that are given in the question? One is the mass of the body and the other one is the momentum. Okay, so I have listed as a part of the solution, I have listed small p, which is momentum, is equal to 3000 kg meter per second, and then mass is 60 kg. Okay, so the moment I read the first line, I can list down these two pieces of information. Now, what is being asked? Number one, kinetic energy of the body. Okay, number two, the velocity of the body. Now, it is common sense for us to understand, for us to know that the body must be having some velocity. That is why there is a momentum value present. Okay, because momentum depends on m and v. Obviously mass has to be there, but the body can always be in rest. Okay, but in this question the body has some velocity, that is why the momentum value has come out to be non-zero. Okay, so let us go ahead. We know the p value, which is the momentum value, we know the mass value. Okay, so momentum we already know has a formula m into v. So m into v is equal to 3000. M value will be replaced over here in place of m. So we can get 60 goes that side, it divides, so you get the value of velocity as 50 meters per second. Okay, so the second part, as you can see, has been obtained first. Okay, now once you know the velocity of the body, you can always calculate the kinetic energy. The formula we already know, half mv square is equal to, so we start putting the values. Half mass we already knew from the question, 60 kg, and velocity we have just arrived at. Okay, so the velocity value we will put, and since there is a square, you go ahead with the calculation, you will get 75,000 joules, because please remember this is kinetic energy we are talking about. Okay, so the SI unit we have used 75,000 joules, or you can also write it as 75 kilojoules. Okay, so that's a simple question based on what we had discussed. Now moving on to the next question. Okay, so continuing with question 2 over here. Now have a look. A spring is compressed by a small trolley of mass 0.5 kgs lying on a smooth horizontal surface as shown. Okay, so the first line, once you have read it, what do we understand from the first line? That there is a spring, okay, that is compressed. Now as shown, so you can have a look in the diagram. This obviously is the spring that you have. It has been compressed. Why? Because the trolley is pushing across against the spring, which is attached to a rigid wall. Okay, so this is your trolley, this is your spring, okay, and this is a smooth horizontal surface. Okay, the trolley has a mass of 0.5 kg, and we are right now ignoring the mass of the spring over here. Okay, so now this is the setup. When the trolley is released, it moves with a velocity of 2 meters per second. So when the trolley is released, it moves away to the right side with a velocity of 2 meters per second. Okay, find the amount of potential energy possessed by the spring initially. Initially means when the spring was compressed. Okay, so now again this is common logic for us, for everyone who has seen a compressed spring, that till the time we keep the spring compressed, it is not in motion, but the moment we release the spring, it comes back quickly to its original elongated kind of configuration, which forces our hands away with a particular energy. Okay, so what is the energy transformation that is taking place? What was the reason why the trolley was not moving earlier, but the moment we released the trolley, it started moving towards the right side? So the theory involved over here is, when the spring was compressed, as you have already studied, what form of energy did it possess? It possessed elastic potential energy. Okay, because somebody was applying some force and hence doing some work on the piece of spring on the spring, keeping it in a compressed position. Okay, so that compressed spring had elastic potential energy stored in it. Okay, now that energy was stored in it as long as it was compressed. The moment you release it, it gets elongated and it comes back to its original shape and form. Okay, so now that stored elastic potential energy has been transferred or transformed into the kinetic energy of the trolley. Okay, now the very important word to note over here is that it is lying on a smooth horizontal surface. What does the term smooth signify here? Smooth horizontal surface ensures, as you can see over here, smooth surface ensures full energy conversion, which is practically impossible in the real life. But then since these are numericals, we can always hypothesize. So this was a smooth surface, frictionless surface. So the entire elastic potential energy stored gets transformed into the kinetic energy of the trolley. Okay, so in order to determine the potential energy possessed by the spring initially, we can always calculate the kinetic energy of the trolley. So kinetic energy of the trolley, again half mv square, mass is 0.5 kgs in the question, and v is already given again in the question as 2, so 2 square. So once you calculate, you get a value of 1 joules. Okay, so the kinetic energy of the trolley, the moment it started moving, it had 1 joule of energy. Now from where did this energy come? Obviously it came from the transformation. When the elastic potential energy of the spring got transformed into kinetic energy, this is what we have got. Okay, so therefore that is elastic potential energy of the spring, which has been asked in the question. Find the amount of potential energy possessed by the spring. So how do we know that the spring had 1 joule of energy? By the simple concept that the energy transformation has taken place. Okay, so kinetic energy of the trolley and the elastic potential energy of the spring, they both are same, and we have already calculated that as 1 joules. Okay, so that is as far as this question is concerned. Now coming down to the third question in this sequence, please read the question. A bullet of mass 50 gram is moving with a velocity of 500 meter per second. So this bullet has been fired from a gun. Okay, so the mass is in 50 grams and it is moving with a velocity of 500 meters per second. Okay, it penetrates 10 centimeter into a still target. Okay, so this bullet, which was moving with some velocity, it struck a still target. Still means stationary target. Okay, now obviously the moment something strikes a stationary target, it is offered some kind of resistive force. Okay, so it starts to slow down. Okay, so as we can see from this statement over here, it penetrates 10 centimeter into a still target and then comes to rest. So what made it come to rest? That resistive force that was offered by the target. Okay, so if somebody comes running towards you and you offer some resistive force in the opposite direction, obviously that person's velocity is going to reduce first and then he will come eventually to a stop. Okay, so that is as far as the understanding part is concerned. Now find number 1, kinetic energy of the bullet before striking. Okay, so before it actually struck the target, we are supposed to know find out the kinetic energy. Okay, so that is the first part of the question. Okay, so here you see the first part, we have calculated the first part, kinetic energy of the bullet before striking. Okay, so before striking there was no resistive force, so kinetic energy simply has a formula half mv square, half. Now here you have to be a little careful because mass of the bullet is given in grams, which is not the SI unit, so we will have to convert 50 grams into kgs. So for gram conversion into kgs, we divide by 1000, okay, into v square, and v value is already in meter per second, so we write 500 square. Okay, so after calculation you will get a value of kinetic energy as 6250 joules. Okay, so this much of energy was being carried, imagine, by the bullet, this much energy was being carried. Okay, so now obviously the person or the thing that will stop the bullet will have to offer a lot of retarding force. Okay, somebody, or in fact over here it is that still target which is actually having to stop the bullet. So for stopping somebody moving with such a kinetic energy, you will have to do some work. Okay, so this still target, if you look at it from this perspective, the entire kinetic energy of the bullet initially was 6250 joules, but after some time it comes to rest. Okay, so this entire kinetic energy is going to disappear. Okay, no, not disappear, because the law of conservation of energy says that energy cannot be created nor can it be destroyed. Okay, so this 6250 joules will not disappear. The only thing is it will be used up. Okay, it will be used up in overcoming that resistive force. Okay, so this entire kinetic energy will have to be equated with the amount of work done by the bullet in opposing that resistive force. Okay, and as you already know, the work done is equal to force multiplied by displacement. Okay, what kind of force is acting over here? This force is the retarding force or the opposing force, offered by what? Offered by the still target. Okay, so F multiplied by displacement is the work done, and that work done is equal to the kinetic energy of the bullet, because the entire kinetic energy has been used up. Okay, so kinetic energy value we already know, 6250 joules. Okay, on the left hand side, F retarding, if you read average retarding force offered by the target is what you have to calculate, multiplied by displacement. Now if you read the second part once again of the question, it penetrated 10 centimeter. Okay, so the displacement was 10 centimeter into the still target. Okay, so this 10 centimeter again has to be divided by 100 to convert it into SI unit, which is meter. Okay, so 1 0 gets cancelled, this 10 can cross multiply over there, so you will get a F retarding value of 62500 newtons. Okay, so this much is the retarding force that was offered. Okay, children, so this is the fourth numerical, again of a different type, that I want to discuss with you all. Please read the question first. These are all questions, by the way, from your exercise. These were unsolved questions. Some of them that I felt need to be discussed, I have discussed. So I expect that you will follow the procedure and you will solve some numericals on your own also. Okay, now let's read the question. A pump lifts 500 liters of water from a depth of 80 meters in 10 seconds. Okay, so there are three informations that have been given in this particular line. We have 500 liters of water. So this is the volume, not the mass of the water that has been given. The depth or the height, if you can call it that, is 80 meters and the time taken is 10 seconds. Okay, calculate number 1, the operating power of the pump. Okay, so the power at which it is operating, and then second one is power rating of the pump if the efficiency of the pump is 40%. Okay, so let us first deal with the first part, operating power of the pump. Now power formula we have already discussed. Power is rate of doing work. Okay, so who is doing the work over here? The pump is doing the work. What sort of work? It is lifting the water up by a particular height. Okay, so we have work upon time, or we can also say energy upon time, because work and energy, they are interconvertible. Okay, so here the change in the potential energy of the water that has been lifted up is mgh, and obviously then divided by T. So if you observe over here, the only small issue that we will face is G has been given, H has been given 80 meters, and the time is 10 seconds. So the only direct information that has not been given to us is the mass of the water. Okay, so the volume of the water will have to be converted into the mass of water. Okay, so how do we do that? You can have a quick look at this small portion that I have done over here. You may do this calculation as a part of the solution also. Okay, so density is equal to mass upon volume is a formula that you are all all very well aware of. Okay, so mass, if we cross multiply density and volume, you will have mass is equal to density into volume. Okay, so why are we doing this? Because we need to determine the mass of the water that we had lifted or the pump had lifted. Okay, so density of water, you must remember in SI units it is 1000 kilogram per meter cube. Okay, so that's the density of water multiplied by how much is the volume of water? 500 liters. But please remember, liter is not in SI system. So this is the conversion. 1 liter is equal to 1 upon 1000 meter cube. Okay, so if 1 liter is equal to 1 upon 1000 meter cube, therefore 500 liters will give you 500 upon 1000 meter cube. Okay, so using this relationship I have converted non-SI system of unit into the SI system. Okay, so now density value is also in SI and volume is also in SI. So once you multiply according to the formula, you multiply 1000 and 1000 will get cancelled. So the only thing that you will get is 500, and meter cube also gets cancelled. So the effective unit that you have obviously is kg, because this is mass that you were calculating. Okay, so the mass of the water lifted is 500 kg. Now as far as the calculation was concerned, this is the way. Now it is very natural for us to know, although I have explained this conversion, you must always remember that because the density of water is 1000 kilogram per meter cube, whatever number of liters of water have been given in volume, that same value becomes the mass of the water. Okay, so the reason why this explanation took place was because had it not been water, then this is the procedure that you would take. So from now onwards, whenever you say x liters of water, whenever you see x liters of water, you can simply write it is equal to x kgs of water. Okay, so 500 liters of water becomes 500 kgs of water. How? This is the way. Okay, so now that we know the mass of the water also, we will simply use this formula and we will put the values. Okay, so mass 500, g value is already given 10, height or the depth is 80 and divided by time. How much time did the pump take? 10 seconds. So after calculation you will get a value of 40,000 watt, or you can also write it as 40 kilowatt. Kilo, K with a small and W with a capital letters. Okay, so this is nothing but the operating power of the pump, the power at which the pump is operating. Okay, now second one, the power rating of the pump or the input power, you can say. Okay, because this operating power of the pump is the output power that it is generating. Okay, so second part, power rating of the pump if its efficiency is 40%. Now let me give you a brief idea of the word efficiency. For all machines, you will study this in the next chapter also in detail. Efficiency is the ratio of the output power to the input power. Okay, and since it is always expressed in terms of percentage, so we multiply it by 100. Okay, so this is the symbol eta. Okay, all this again you will study in the very first video of machines. So as of now, please remember, efficiency is equal to power output upon power input multiplied by 100. Okay, so now putting the values, efficiency value is given as 40, so we will write 40 over here, is equal to power output we have already calculated as our operating power in the first part, so we will write 40,000 watt. Okay, so 40,000 divided by, obviously power input is what has been asked, power rating of the pump is nothing but your power input. Okay, so into 100. P input comes here, 40 goes that side. So once you calculate, you will get the input power rating, which is also known as the power rating of the pump, comes out to be 1 lakh watt or 100,000 watt. Okay, so that can always be converted into kilowatt. Once again, it is going to come out to be 100 kilowatt. Okay, so this is as far as the efficiency related questions are concerned. Okay, so I think that most of the difficult questions have been discussed, the different types. Okay, so now I expect you all to be familiar with the second chapter. Please read the theory, the conversions, the transformation of different forms of energies, one form of energy into another form. Okay, what are the different devices what sort of energy conversions take place in them. Okay, so all these things you have to read from the book. Okay, so I expect that you will solve a few numericals also. Okay, thank you.